Okay, so here I'm going to talk about hash tables, and hash tables are used to store data that you're frequently going to be performing searches on. So maybe you work for a company and you need to search how many things you have in stock based on a product number. We know that there are searches available like a linear search, which is on the order of n, which is not great. Or binary searches, which are on the order of log of n, which is a little bit better. But with hash tables, the primary search operation is on the order of 1, which is much over either a binary or linear search. It involves a lot with the mod operator. So if you are still having problems with the mod operator, you can go into the calculator. If you're in the scientific view, right, you can change your view from standard to scientific. You do have a mod operator here, so you can say like 8 mod 9 is 8, right, which actually is the correct answer. Or let me just see here, scrolling around my calculator. Well, you get the idea. So if you need that, you can use it. If you can't do that math in your head. Okay. In the examples that I'm going to demonstrate, I use a table size or an array size of 13. There's been a lot of proofs that prime numbers create more efficient hash tables. And what you do is you use a hash function. This is probably the most common hash function would be to take a key value, and a key value has to be a unique number, right? An employee number, student number, product number. And it may be part of a structure or a class object that's stored in the array, but the key is what you're using here in this case. And what you do is you take the key value and you hash it to an index in the array. So for instance, if the key value, I'm just using simple ones, was 5, and the size of our array is 13, then this particular element, right, with this key value would hash to index 5. Or 0, right, 0 mod 13 is 0, so that would go at index 0. 11 mod 13 is 13, so 11 goes here. 17 mod 13 is 4, so that would go to 17 would go to index 4, and 27 mod 13 is 1, so 27 would go at index 1. And that's a basic idea behind a hash table. And you can see that why it's on the order of 1. When you put it in, it's on the order of 1. When you insert it, when you search for it, like you could say, is 27 there? Well, 27 mod 13 is 1, so I'm going to go to index 1, and I'm going to look and see if it's there. So that insert operation and the search operations are on the order of 1. The removal operation is also on the order of 1, and I'll talk about that in just a bit. So that's an easy example, but what happens if you also had a key value of 4, and 4 mod 13 is 4, but we already have something stored there, and that's what's referred to as a collision, when two key values hash to the same index. So hash tables need to have a way to handle collisions, and there's 3 different ways to handle these collisions, using what's called chaining or linear probing or double hashing. So I'm going to explain each of these. With chaining, each element in the array is really a pointer to a linked list. These are just little linked lists out here. So if a collision occurs, you add that new key value to the end of the linked list. So I started with the same initial array with 0, 27, 17, 5, and 11 already in there. 0, 27, 17, and 5 and 11 were already in there, and I added some new values. So 26 would hash to index 0. Oops, I gotta change that in my document, right? So 26 would just go in this linked list. Okay, 15 mod 13, if the key value is 15, it goes to index 2, and it just gets put in this linked list. 18 mod 13 is 5, and there was already something at index 5, at 5. We had a key value 5 already, so we just add 18 to this linked list. 24 mod 13 is 11, and again we already had something at index 11, so we add 24 to the linked list. And 39 mod 13 is 0, so that gets added to this linked list. This is relatively efficient, and if you think about it, if you insert something, even if you're inserting, 3 nodes in a linked list, it's still on the order of 1. If you go to remove something from a linked list, if you want to take it out of the table, it's probably still on the order of 1. And these linked lists probably would be better as a double linked list because it would be easier to remove them. And the search operation, same thing. If I'm searching for, for instance, 18, I would go to index 5, and if it's not here, I would just keep looking, and I'd have to look at 2 nodes. And a lot of this has to do with what's called the load factor of the hash table, because hash table, you don't want it to be completely full. If it's completely full, or too small, you're going to get large chains of linked lists. And that load factor is addressed in a section of the Zhai Book, which I'll talk about. Okay, so that's an example of chaining. Now, linear probing is another way to deal with collisions. If the collision occurs, right, there's something already there, you just look to the next element in the array and see if you can put it there, and if you can't, you look to the next element, etc., etc. So this started with the same initial array, right, from here that had 0, 27, 17, 5, and 11 already in it. 0, 27, 17, 5, and 11 is already in it. And I'm thinking that, maybe I should just shade these guys. Just to show you, sorry, I shaded them just to show you what was originally there. And I went back and shaded these original elements too. So here's the new stuff I'm adding. So 26 mod 13. That hashes to index 0, but there's something there, so we look at the next element, there's something there, so then 26 would go right here. 15 mod 13 is 2, but there's already something in 2, so I go to the next element and then I put 15 in. 18 mod 13 is 5, but there's already something at index 5, so I'd put 18 in the next element. And then 24 mod 11 is 13, and 24 mod 13 is 11. There's already something there, so we'd put 24 here. And this is what's referred to as linear probing. So the insert operation is just pretty much on the order of 1. Even if you have to look through a couple of elements, it's still on the order of 1. To find something, right? Let's say I wanted to find 15. I know that hashes to index 2. And if it's not here, then I can just look at the next element to see if it's there. And it is, okay? And removals, again, I'll talk about in a minute, but they're also on the order of 1 or a few minutes. The problem with linear probing is that it can lead to something that is called clustering. Okay, clustering is when you get a bunch of elements all next to each other. And if you think about it, if I tried to add like 39, it would hash to index 0, but that's full. So I'd have to look here, and that's full. I would have to look here, 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 and then I have to put 39 all the way down there. So to make a more efficient hash table, you want to kind of, when you do have a collision, or when you're putting things into the hash table, if you don't have these clusters and you can spread things out more, that's a little bit more efficient. And the last way to deal with these things is what's called double hashing. And this is similar to linear probing, but with linear probing, if it's not the index isn't available, we just increment it by 1 and look at the next one. With double hashing, you actually have 2 hash values and a calculation that occurs to find the new index. So we still use our same original hash function, but we come up with a second hash function in addition. And you'll notice I'm using 13 and 11. 13 and 11 are considered to be twin primes. A twin prime is when you have a prime number and 2 less than it is also a prime number. And a lot of times twin primes are used in hash tables because there's been a lot of mathematical proofs that show that they lead to less collisions. So if you think about it, like 31 and 29 are twin primes, and there's, I think, like, I can't remember, there's 837 and 835 might be twin primes. Don't count on that. That's just something that's in my head. So there's probably something close to that that's a twin prime. So you apply this big, long hash function. So we had our original values, and again, let me just, for the purposes of this, let me highlight or just, denote to you what was in the original one and where the new values go. So this, when I is 0, and you can see up here in this formula, you're going to have I times this whole thing, so that's going to be 0. So it's just really, key mod 13. So it's just doing the same thing we did originally. So 26 mod 13 would be 0, and there's something there. So now we increment I to 1, and you can see that I filled in this whole calculation here. The key is 26 mod 13 plus I is now 1 times 11 minus the key value mod 11, the whole thing mod 13, and then you do all the mathematics behind it, and you would get index 8, and index 8 was available, so I put 26 there. You could see if there was something already at this index, I would increment I to 2, and I would do this calculation again. So with 15 mod 3, that goes to index 2, and that's available, so I put that here. 18 mod 3 is 5. I'm going to have to fix my whole calculation. What did I do here? 18 mod 3 is not 6. All right, I'm going to pause it and fix my numbers here. Okay, so sorry about that. So I revised this whole thing. So something was at 5, right? Something was already there. So again, now I have to apply this whole additional, calculation here. And this will eventually evaluate to index 9, and nothing's at index 9, so I'm going to put 18 there. And then 24 mod 13 is 11, but 11 did have a value, so again, apply this calculation, and that brings us to index 7, and that's where we put 24. So as you can see from the first example with linear probing, this generally leads to less clustering. It's, it's kind of hard to see because it's a tiny array, but not everything is all together in one big cluster. Okay, so now I'm going to go to into the Zhai book. Okay. And in the Zhai book, it also explains a little bit more about the remove process. The remove process is relatively easy with chaining, but not so, there's a little bit more to it when it comes to linear probing, and also double hashing. So in section 11.3, it does talk about the removal process, where you kind of have to have, it's empty since the very beginning of the process, or it becomes empty after you remove something, or it's occupied. And this really does explain it pretty good, so I'm going to let you go through this section of the Zhai book, but the idea is, if you remove something, you have to mark it in a special way. And even if it's just like Sometimes empty since start might be -1, empty after removal might be -2, and occupied might not have anything in it. So I mean, it could really, or occupied has something in it. It could be really easy. But what happens is if you take something out of the hash table, you have to mark it that basically you remove something from that location. Because if you go to look for something else and you use linear probing with that value, you need to know to look to that element. And if it's been marked as being removed, you got to keep looking to the next element until you find yours, until you find a space that's been empty since start. So I'll let you look through this process in the Zhai book, but basically, just to reiterate, there's three main operations in a hash table: putting something in, taking something out, and searching. Searching is the big thing. And they're all really on the order of 1, which is super efficient, especially when you compare them to other searches, such as a linear search or a binary search. And lastly, I just want to comment, let's go in here. I didn't assign anything in this common hash functions, but you might want to just take a quick peek at this. It talks about the modulo hash function that we're using, but it also talks about other hash functions that can be used as well. And they can get very complicated mathematically, but if you're interested in looking at that. And the other thing that I talked a little bit about was the load factor. And this talks about how you can resize a table and when to resize it based on the load factor. When you're working with chaining, you might be able to have smaller arrays for hash tables, but when you're working with linear probing, double hashing, your arrays have to kind of leave some space in them. If you have 100 things that you're putting in them, you might want to consider a load factor of like 50%, so having an array size of 200, but this talks a little bit more about that.